Is it the same computer lab that we have been using?
The same.
Okay, they just adjusted the angle of the camera a bit.
Yeah. But it's the same. The same place, the same lab. We'll have Klaus today. Yeah.
Sorry?
Klaus will join us today.
Yeah. He will be joining for the last session.
Although a lot of trainees didn't come yet, however, I prefer to start in time.
Completely agree with you, Dr. Samir. Then the remaining trainees can just either sneak in without disturbing or wait for the break to join.
Okay. Okay, let's start, Matt, please.
I will. Thank you. And once again, welcome to everybody for this third training session in the wave modeling, the Mike 21 SW. Today, you already know Dr. Samir. You already know Engineer Ruben, who presented last time. Ruben will once again continuing his presentations on the more technical part, among others. And late today, we will be joined by Engineer Klaus Bundgaard, who is our key expert as coastal engineer. Klaus has, I guess we all lost count, but he has several years of experience in modeling in general, wave modeling in particular. He is currently the head of our coastal department, and he will, by the end of the day, give a presentation on common faults and pitfalls experienced in Mike SW modeling, based on his many years of experience. So today, that's the third session of in total 4 training sessions, where the fourth session is spanning over 2 days. So after today's, there will be 2 more days of training in the level 1. And the subjects of today is, or the purpose is an introduction to data collection. So we will come up and give you a presentation of where data needed for wave modeling can be gathered and how it can be utilized in the wave modeling. Yeah, and then I said some more theoretical presentation by Ruben, and then a general walkthrough of the modeling in general. So these purpose and job subjects should be reflected here in the agenda or the program for today. We will of course start up with a small recap of the training we had. That's 2 weeks ago now. So maybe good for everybody to just wrap up what we covered in the last session. And then we have these 5 presentations, where in between I still expect, Samir, please correct me, but there will be some sort of training tasks associated with some of these topics. Otherwise, you will have plenty of training activities in the next two coming training sessions. So yeah, there should be plenty of material to covering today, the day of today, and I expect it to be interesting for you all. At least that's my hope. So I think I will give the word either to you, Ibrahim, first, if you want to say a few words.
Yes, just I wanna welcome everybody in the lab. I'll make it in Arabic to make it easy for them. برحب بحضراتكم طبعا. والنقطة هنا إن هذا التدريب على الويب موديلنج هو بالنسبة لكم فرصة جيدة، لأن إحنا عندنا وقت سواء النهاردة أو اليومين اللي جايين إن شاء الله في السيشن 4 هيبقى عندنا وقت إن كنتوا تعلموا كل حاجة أنتوا عايزينها من الدكتور سمير. فيا ريت لو في أي حاجة أنتوا أخدتوها نسيتوها أو عايزين أو لسه محتاجين فيها تدقيق بعض الشيء، الدكتور سمير مع حضراتكم وهو مشكورا يعني هيديكم كل اللي انتوا عايزينه. فحاولوا يستثمروا وجوده النهارده واليومين اللي جايين ان شاء الله، الاسبوع الجاي والاسبوع اللي بعده، بحيث تطلعوا من هذا التدريب. عن يمكن غيركم في السيشنز الثانيه، التدريبات الثانيه ما عندهمش الوقت اللي موجود للويب موديلنج، فدي فرصه بالنسبه لكم. يا ريت الله يحفظكم. زي ما قلت قبل كده انتوا الاسد بتاعنا بعد كده، بتاع مصر يعني، مش بتاع المعهد ولا بتاع المشروع، بتاع مصر اللي كنتوا هتعملوا الموديلنج. فيا ريت تفهموه كويس قوي من الدكتور سمير، سواء اللي فات لو كان عندكم نقص ولا حاجه، او كان عندكم اي اسئله يا ريت تاخدوها تاخدوا اجوبتها من الدكتور سمير النهارده. اذا ما كانش فحاولوا تركزوا النهارده في اللي هيقوله وتركزوا على العملي في الشغل. وعندكم زي ما قلت لحضراتكم يومين كمان ان شاء الله، الاسبوع الجاي والاسبوع اللي بعده في هذا النوع من التدريب. التدريبات الثانيه ما فيهاش هذا الوقت اللي هو اللي بيسمح بالتدريب العملي. وحضراتكم مع خبير دكتور سمير، راجل من خبراء الموديلنج في مصر المعدودين، على ذاتي انا عشان هو موجود، لكن هو فعلا من خبراء المعدودين في الموديلنج في مصر. وده اساس شغله يعني، ده كموديلنج. يا ريت تحاولوا بقدر المستطاع تاخدوا منه اللي انتم عايزينه النهارده والاسبوعين اللي جايين ان شاء الله. اتمنى لكم التوفيق، اتمنى لكم ان شاء الله بيوم مثمر في هذا التدريب. ربنا يوفقكم. شكرا جزيلا. Thanks, Matt.
Thank you very much, Ibrahim. And then I guess we are ready to start the actual program of the day with the recap of yesterday's training. And unless you, Dr. Samir, will say a few words as well.
I forget to welcome two new trainees from today, Engineer Ibrahim Mahmoud and Engineer Ahmed Salama. They are come with us today and start the training with us. And I believe that they have good experience, previous experience, and they can continue with us in the same session. Okay, would you like to start, Robert, to recap the previous training? Robin?
Mm-hmm. Okay. Please, you just take over the presentation, Ruben.
Yep. So let me. I will open my presentation from last week. Part 1. Okay, so let me share my screen for a sec. This should be quite fast. So basically, last week or 2 weeks ago, what I had time to do in this wave theory introductory course was I was focusing on the first part of my presentation, which was basically what are waves, how can we mathematically model those waves, whether they are regular or irregular, and then how might interpret all of that information to be used as input and then compute more waves. So this is, as you know, Mike is a wave transformation model that needs of some boundary conditions in the form of waves and winds. And once we impose those boundary conditions, those waves along the boundary, they are transformed, taking into account all the physical processes that the waves undergo. And then you will get the transformed energy of those boundary waves in any location within the model domain. Good. So if we do a quick recap, the other day I was explaining to you what the difference between a regular wave and an irregular wave. A regular wave is basically what you can find in a laboratory in a flume, whereas irregular wave, which is the superposition of many, many, many regular waves from different directions and with different frequencies and blah, 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 is what we call an irregular sea state, or what we see out in nature. Every day we go out and see and take a look at the coast. We also define what a very important, or two very important concepts in here, that were what a sea state is, and equally important, what the wave energy spectrum is. And while describing the wave energy spectrum in here, I was telling you the two different types of spectrum that you will encounter, professionally speaking. The first one is the 1D spectrum, which is a spectrum that has been integrated over direction, and you only get information about the distribution of the frequencies, of the energy within the frequencies in that sea state. But it does not tell you anything about how in the space that energy is distributed and is pointing towards. If we get a full 2D spectrum, we will have that information. At the same time, we will see where the energy is coming from. So this is the most, a 2D spectrum is the most reliable way of describing the energy within a sea state. And last but not least, I told you that a wave spectrum can be obtained from a time series of measured sea surface elevations by means of the fast Fourier transform. And likewise, starting from a spectrum, you can apply the inverse of that fast Fourier transform and get a time series. So the both concepts are interconnected. All the things that I showed you today is were basic and basic definitions of the parameters that you can get from analyzing, from observing the 2D spectrum. And these are parameters that you will be using in coastal engineering every single day. So it is very important for you to have these concepts clear in your mind, which are the significant wave height, the peak wave period, the peak wave frequency, and the mean wave direction. I was also explaining to you that theory is very nice the other day, and then for simple sea states, or for areas where the waves are coming basically from one direction, a theoretical, if you don't have enough information, a theoretical wave spectrum will do the work for you in order to represent the energy of that sea state in a mathematical grid of directions or frequencies. But if you are in an area where it's more complicated, where you have many, many, many different sea states, sea systems coming from different directions, then what you get is the image to the right, a way more complicated spectrum that cannot be represented by any theoretical expression. And for this, you will need to have access to either measure buoy data or fully modeled and saved spectral information. Good. So after this, then we went into what Mike can compute, or what is it that Mike do. And then I was explaining to you that basically it takes as an input those sea states that you are selecting, either by imposing a wave spectrum, or if you don't know the wave spectrum, you apply integrated parameters, and then Mike internally will convert those integrated parameters that define a certain sea state into a frequency and direction grid or a spectrum that can be modeled by Mike. So basically, Mike will take each of those little cells in your 2D spectrum, will simulate the transformations from the boundary to the target point, and then it will reconstruct the signal once all the little chunks, all the little energy cells have been propagated to the target point. And the last concept that I showed you about this was in the case that you don't have wave spectra, real 2D spectra at the boundary to impose how much energy makes it into your model, I was showing you what Mike does if you don't have that information. So if you are starting basically from, I just know for this time, the significant wave height, the peak period, and the mean wave direction. So based on that information, what I was telling you is that this is what Mike is going to do. He's going to assume a certain theoretical profile or theoretical expression for the energy. which is basically dependent on the frequency. And then regarding the energy, I told you that the energy, although you have a mean wave direction, it does not mean that all the energy goes all the time in the same direction. It means that both sides of that mean direction, you will have some spreading of the energy, because waves go a bit, they have differences of 1 degree, 2 degree, whatever. So the thing is that Mike has to make use of dispersion function in order to give to that 1D spectra or energy spectra the 3D part, or the third degree of freedom. Let's say the surface. You can see how the energy is spread in the space. And with that, Mike will start, as I said again, chopping that wave energy spectrum in cells of frequency and direction. It will model each of those, will recompute at each of the target locations or nodes, model nodes, and then it will output the transform waves. Basically, that's what we did last week. I hope that it was fully understood. And in case that you have any questions or you need more, a better description of what was presented here, please contact me. Okay, so Dr. Samir?
Is there any question related to the topic?
We need more explanation about the transport information.
Excuse me, can you come and give your question?
Yeah, I cannot hear.
Yes.
Okay, we need more explanation about the transport equations used to calculate the wave energy.
You would like to get more information about transport equation used to model the wave energy.
More information about the equation.
Yes.
So about this one. So basically, this is the equation that Mike solved, and this is what we call the wave action density. And the wave action density is defined by this letter n. And what is this letter n? This letter n is basically, for a given C state, is your 3D or your 2D spectrum. So you see this circle in here, this discretizing frequencies and directions, and all of those values of energy density in that spectrum are divided by something that we call the intrinsic frequency. And why do we do this? It's very simple, because you may think of the waves carrying energy individually. So each wave has a certain wave height, and because you have a wave height, it has an associated energy. Right? The energy of a wave is proportional to the square of the height. That's simple. But what happens that the waves in irregular fields, they do not travel alone or independent from the other waves. There are some rules imposed by the what we call the dispersion equation that makes that waves travel in groups. So waves with similar frequencies, they tend to travel together in what we call packages. And what happened with those packages? That those packages, the energy of all of those individual waves, as an average, we can say this way, that energy travels with what we call the group celerity. It's not the wave celerity, but the group celerity. And one of the consequences of that is that that energy is preserved, whereas the energy of a single wave height is not preserved. This is talking about reference systems. It's just talking about reference systems and how the models treat the data. So you don't have to give this a more detailed, to pay more attention to this than it is. It's basically just a way of making sure that you preserve the energy in the C state. So having said this, basically that letter n is your input spectrum divided by a single number that is calculated by the program, and it has to do with the group celerity, which is dependent on the peak period, and it's also dependent of if in your simulation you are applying a current. Those currents will push your waves, and as they push your waves, if you have a spectrum, you will see that that spectrum is kind of squeezed or expanded because the current is pushing those waves, and it's creating a relative motion between different reference systems. So that's why it's so complicated, but it's just a number that is computed by Mike, and then it solves that equation. So you can understand that it's just your input spectrum divided by a certain number, and then this equation tells you what happens. So for example, the first term is telling you how that action density varies within the time. The second term, it tells you how that energy that you're considering, that little package of energy, for example, this is that the Mike is modeling right at the minute that you're taking a look at this equation, is telling you how it propagates within the domain, because here we are the group celerity and the current velocity. This other term is telling you how the energy is redistributed in that C state, or in that little energy cell that you've got, based on the ambient frequency. Or this is in case that there are some currents at the same time that you're modeling waves, it will tell you how those currents are affected. Yes?
Just wait 1 second, few seconds.
Yes.
Please make your presentation full screen.
Full screen.
Yes.
I thought, is it this one?
Yes.
Okay. Now it's full screen right now.
Yes, but was view من عندنا ولا من عندكم؟ في view عندنا هنا اهو. الفيو ده. فوكس فيو كده. في المفروض كمان هنا امكانيه بس المنيو مش موجود هنا. Okay, go ahead, please.
Okay. So I will not bore you with more details of the equation, but basically what you have to pay attention to this equation is you have two sides in the equation, right? You have the left hand and the right hand. If you take a look to the left hand, you will see that the letter N appears in all the terms. What does it mean? That the left part of this transport equation is telling you what happens to the energy that you're imposing in your model. So you are imposing a certain spectrum with frequency and direction, which has been converted to a quantity called wave action density. And then the left part of the equation is telling you how that energy evolves within the model. And then you have the right side of the equation. And then the right hand side of the equation is telling you the energy sources and sinks. So basically, the right hand of the equation is telling you all the processes that the waves that you have to the left of your equation are going through. So again, all the terms in the left part of the equation are just about how the energy within the same C state interacts with different frequencies from its own C state, and they evolve. And in the right hand, you have effects like, for example, what happened to the waves when the wind is blowing? If it's blowing in the same direction as the wave, basically it will create wave growth. So the energy in your system will be growing. Or the opposite, if the wind is blowing in the opposite direction to that wave that you are modeling at that moment, you will have shoaling, or you will have breaking, or you will have white capping that will take out energy from the system. Other things, as waves travel in deep water, they will not fill the bottom, and then there will be no dissipation due to the seabed. But as the waves start going into the continental shelf, and they start filling the bottom, when the waves interact with the bottom, they will go under friction. And due to the friction, energy will dissipate, and the wave height has to lower down. So basically, that's what this equation, that's what Mike does. In the one hand, it tells you for that little energy package that you're considering at that moment of the simulation, it will tell you how, just based on simple physics, that energy will travel. Accommodating to the local bathymetry that you've got in your model, it will tell you how it moves towards the target location. On the right hand, it will tell you on the way from the lateral boundary to that target location that you're looking at, what happened. If it encountered a lot of shallow water, if there was a lot of strong wind blowing in the same direction, or you have crosswind, blah, blah, blah. And in the end, that equation gives you an energy balance. All the energy that you are imposing in the model, it has to be balanced with all the energy that you are imposing in the model due to wind, for example. And also all the energy that you're taking out from the system due to braking or seabed friction, for example. Was this a bit clear, at least for the concept?
Okay, thank you, Robin.
Good.
I will start now recap my my previous training day. Okay. I will share my screen.
No. سمير احنا شايفين بس القاعة لكن مش شايفين السكرين بتاع حضرتك.
مش عارف انا الشير هو ما بيشتغلش
حاول بس تشير السكرين معانا الله يحفظك عشان التسجيل بس عشان التسجيل.
Now can you see it? شايفه دلوقتي ابراهيم؟
لا دلوقتي خلاص شايفين كده خلاص.
كده؟
نعم.
اشتغل بابلكيشن اللي هو اوكي. In my previous training day, I was talking about the what I would say Egypt Atlas, Egypt Wave Atlas. We talked about the wave model we developed, and I would like to rename it as the first atlas for wave in Egypt. This atlas covers all the north coast with 80 points. All the north coast points, as you may watch now, and starting from the global Mediterranean Sea model. This is called the global Mediterranean Sea model, which cover all the Mediterranean Sea. Then we yes. All what I'm going to present is hand cast model. Derived from the wind, yes. So the global Mediterranean wave model, this is the global Mediterranean wave model, and we focus only on Egypt north coast. So we derive something called regional wave model. And this regional wave model divided into three main models. The first part is Matruh, second is Delta, and the third is the North Final. So we have three regional scale wave model. The boundary condition of these three regional scale wave model is derived from the global wave model. Then, in general, in this project, we divide the North Coast into coastal units. Mainly, we have 6 coastal units, and every coastal unit divided into sub-unit. So we export all the information at 80 points selected for detailed output over all the North Coast. We selected around 80 points. The distance between each two successive points is around 0.1 degrees. Around an average 0.1 degrees, as you may show, as you can see now. Some point, special point in front of port site selected. At each point, we plot and we watch figures for time series, which is the 5 parameter points of DFS0. It includes spectral equivalent to significant wave height, maximum wave height, peak wave period, mean wave period, zero crossing wave period, wave energy period, peak wave direction, mean wave direction, direction standard deviation, all these outputs, plus in the other file spectral points.dfsu, the wave spectrum. We have 48 directions. We standardize the wave into 48 directions, and in every direction we divided it into 24 frequency from starting from 0.055, and the output for wave energy and wave action density. This is the output sample for the wave energy. This is a plot for wave energy. At the 80 points, you can select it, which point you like. And at every point, we have 1,152 values at every hour for 41 years, total of around 300,000 hours, which is 41 years at the 80 point. Starting from 41 years from today, 79 as far as I remember, 79. In the figure now, it will be shown. And the following parameters, I mentioned that these parameters, all these parameters, we have the time history for 41 years for all these parameters at the 80 points. And then we discuss the different types of wave analysis done in the data. We talked about short-term analysis and important C-state parameters, and long-term analysis for normal conditions, and long-term analysis for extreme conditions. This is starting from 1987 up to 2020. This is one of the, as example, one of the analysis, which is the annual average and long-term monthly pattern at the delta costs. This shows the mean water level surge due to surge with time for the 41 years, which shows that this there are increase, linear increase, and we can detect the equation using Excel.
The source of the data from? The source of the data from?
This is the results of the model. The regional model. And there are a lot of things in previous training. I showed a lot of details about the statistics and joint analysis and tables and so on. This is what happened last day of training. Okay. Is there any questions? Or? Okay.
Calibrated with the data available in the instruments.
There was a calibration done, and the details of this calibration report is already obtained a few months ago. Calibration based on the data delivered to DHI from PMU, and another calibration set from the satellite measurements, many data, and all details of calibration exist on the.
All the 81 points extracted from the original wave.
Yes,
every Egyptian cost. Then we must use it to get the sub numbers.
We have 3 regional models, and we extract the output at 80 points from these 3 regional models. Okay. So if you would like to make any local simulations, we are going to take the data from the 8 points based on the location we are talking about, and use these points to simulate. Yes, to simulate your localized area. Okay, Robin, Aidan, would you like to start now your session? Robin?
Yes, I can do.
Okay.
I can go with the second half.
Yes, you can start now your.
Okay, so let me open.
Yes.
Okay, let me share my screen. Okay, can you see my screen?
Yes.
Okay, so as we have said early this morning, my presentation 2 weeks ago, this was the original syllabus or the original content of my presentation, but due to time constraints, I couldn't go beyond section 3. So today, what we're going to do is we're going to have a look at how all of this knowledge that you got about the basics of C state and the wave spectrum are applied to Mike. So I'm not going through all the options that you have in Mike SW when you set up the model. I mean, you know, when you have to specify your domain, the time and duration of your simulation, and there are other parameters that describe the model that we are not going into them because they have nothing to do with waves themselves. So I will be paying attention, or I will be focusing a bit more on the options that are critical or important for waves themselves. Okay, so the first thing is once you set up your SW model, when you go into the section talking about the basic equations, you will have an assortment of options. The first option that you will find will be the spectral formulation. This is up to you. You have to decide how you want to run the model. Do you want to have a fully spectral formulation, or do you want to have a directionally decoupled parametric formulation? What's the difference between those two? So basically, the first option was available or was set up back in the days, 20 years ago or something like that, when computing power was not at its peak. So you had to do a lot of assumptions, or you had to put down the computational cost. So, and there was this way of creating your, as I told you the other week, on how to create your 2D spectrum or your spectrum of frequencies and directions in order to be fed into Mike, and Mike will transform that energy. So basically, in the first approach, what this was doing is that if you take a look to your 1D spectrum, this is the frequency spectrum. This is the, for example, a Jones swap. The way all of those energies within that frequency spectrum interact between themselves. The lower frequencies interact with the higher frequencies, blah blah blah, and how the dispersion of energy, both sides of the mean wave direction, is treated. So if you go for section 1, what it will do is that Mike will interpret the joining of your energy spectrum and your dispersion equation in a different way. So each of those packages that are going to be simulated will not interact non-linearly with each other. That's something that was needed to do 20 years ago, but nowadays computers are so powerful, even a regular laptop, any of those that you have in your in the room right now, can do the computation. So without having to do any kind of assumptions of energy on energy transfer, blah, 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 it will compute absolutely everything that is inside or within that C state that you are considering. It does not mean that you cannot use option 1 if you want, but option 1 is basically recommended, as I say in here, only when you have a very small domain. So let's say that you are modeling, for example, a Bay area. So you're modeling a whole bay, but then what is happening at the entrance of the bay, you have your boundary conditions already taken from another model, from a global model, for example, or a regional model, or another mic model that you set up for the area. And if your domain is very, very small, we're talking about 5 kilometers, 7 kilometers from the coast to the offshore boundary, no more than that. In that case, the domain and the time that it takes for the waves to travel from the boundary to the coast is so small that the assumption of doing the directionally decoupled approach is valid. And your model will run way faster without compromising the results. But as I said again, this is only suitable or needed or applicable if you are modeling a small area. If you are modeling a big area that entails going offshore to something like 50 or 100 kilometers offshore, then this approach is not advisable. Good. Then you will have to choose between time formulation. Time formulation, you have both in stationary formulation and quasi-stationary formulation. And this is very important for you as well. The main difference between these two is that in stationary will take way longer to run than quasi-stationary. But what's the catch? That you can only use the quasi-stationary formulation when you have a small domain. And why is this? Because think that you have, let's say that you're imposing a time series of sea states every hour at the boundary. And you have a very, very little model that covers, I don't know, let's say 3 square kilometers, extremely small. So what happens in there? That you impose your first time step as boundary conditions. And then those waves travel from the boundary to the coast. The following time step in your forcing is 1 hour after. But what happens? That your domain is so small that the waves, the time that it took for the waves to travel from the boundary to the coast is smaller than the time resolution of your boundary, of what you're imposing at the boundary. So what happens? That basically that transformation of waves from the boundary to the coastline is instantaneous. So what happens? That when the new condition, the new boundary condition enters the domain, the previous sea state that you were modeling or imposing at the boundary has propagated already. So you don't have to interact with different things that are happening at the boundary and with what happened at the coastline, because everything has happened in so little time that you can consider it stationary. And each time step can be taken as independent from the previous one. But what happens if you are in a domain or in an area that it's, I don't know, 100 kilometers long from the coast? But let's say that you have, again, a resolution of 1 hour in your forcing, and you impose that forcing. And after 1 hour of computational time, the waves at that boundary, maybe they have very long periods, they may have traveled, I don't know, 50 kilometers within the model domain, 60 kilometers. I'm just giving a number. But what happens that when the following hour of your boundary conditions happen, when you have to impose new arriving conditions at the boundary, the waves that you were simulating in the previous step have not yet arrived or have not covered the entire model domain. They haven't had time yet. And what happens that in that case, you have two scenarios, or you have two things going on in your model. One is the previous time step waves that are still traveling, but at the same time, you are updating what is happening at the boundary. So you cannot say that what is happening within the domain in the previous step is completely consistent with what is happening at the new time step. So you have things changing at the same time because your model is so big that has to take into account those things. And that's the reason why when you are in a big, we have a model covering a big area or a long distance from the shore, you cannot use the quasi-stationary solution. You have to go for in-stationary. It does not mean that if you are constrained by time or by budget in your project, you cannot run quasi-stationary in a big model. You will be able to. Mike will allow you. But you have to bear in mind that it's more than likely that when you compare the results from a certain amount of stationary runs, sorry, with, for example, local data that you have measured, you may have you may see a difference. And just because you made the wrong assumption of considering the model was stationary when it's so big that it should be non-stationary. And last but not least, regarding settings, these are just different formulations that have been developed over the years by different researchers, and it tells you, or it grants you the power to choose or to impose how big the waves can go and how fast the waves can grow with the wind. My approach or my recommendation for this, if you're using Mike 21 SW and you are going to model a regional area, at least, even if you will need some data, you will need to extract data near the shore, I would recommend you to use the default formulation of WAM cycle 4. And why is this? Because WAM is a global model. It's a well-known global model, ocean model, that basically it covers the whole world, and it tells you how winds generate all over the world just based on the wind. And this formulation, the one that WAM cycle 4 uses, is the most widely accepted and the one that has less bias and less, when compared to measurements, is the most reliable one. Maybe if you are working in very, very, very shallow water, this is not the best formulation. But as a general case, and based on the standard models that are needed in coastal engineering nowadays, I would recommend you to go with WAM cycle 4. Again, if you change this option, you can do a sensitivity test, and then you will basically see how important the wind is when you are inputting it in Mike, depending on the formulation that you have. But I will leave it as WAM 4. Another one, this one is also tricky to understand, so I will tell you that based on my experience with Mike over the years, I would basically say that apart from the space discretization that you can define, the other 4 numbers that appear there, the number of levels in transport, sensor, I would not touch them. So in here, in solution technique, this is the concept that you need to manipulate and to understand very well. You have 2 options to run Mike. Once you have your input and your mesh and everything, and you know what you want to compute, it is time for you to tell Mike how do you want to do that. How much time you have to do that? How accurate you want to do that? If you want to have, you need results very quickly for you to have an idea on how things, in general, may look at a certain area. You may want to go for the low order or fast algorithm approach. So this is just down to computational stuff that goes beyond my comprehension on how Mike has been set up internally. But basically, it's a way of solving the equations for all the nodes that you have in your mesh, that it simplifies the calculations by means of a diagonal. I can't remember what. The thing is that the computational time is way faster, but at the expense that, especially in intermediate and shallow water, the answer is not going to be as accurate as possible. And this is what I'm showing you in here with this example on, for example, a function that we've got with, let's say that we've got this function cosine x, which is displayed in green. And now what we're going to do is we are going to simulate, or we are going to try to reproduce that cosine signal by means of a Taylor expansion. I will assume that all of you have worked and you know what a Taylor expansion is, which is basically just decomposing or trying to reproduce a certain signal just by means of summations of its derivative. So basically what it is saying in here is that, for example, if we try to approach that real function of cosine by just 4 terms, what we get is the approach plot in red dot. So we see that it kind of resembles, it can capture a fourth of the cycle, but for the rest of the signal, we see that it's rushed. What happens? That you only here have to compute 4 terms. So the computing of those red circles is like this. But now you say, I want to be a bit more accurate, so let's add more terms. Let's be even more precise. So what you see here, that as you increase the number of terms that your program has to calculate, you are getting to something that resembles much more the reality. But what's the problem of this? That you have to perform more calculations, and if you have to perform more calculations, it will take you more time. If you are with a calculator, you will have to repeat an operation 10 times instead of one. Of course, it is slower. But in return, what you get is a more realistic or accurate number. As simple as that. So now it's up to you. You have to check your budget, and you have to check the time that you've got to do the simulations, and select a propagation scheme. And then you have to report the assumptions that you are considering if you go with one approach or the other. Again, the other four numbers do not fit unless you have a very good reason to modify those numbers. And I have to say that in my vast experience, I never found a reason to play with these numbers. Don't play with it. Following one is spectral discretization. Well, I spent a lot of time last week introducing you to what a wave spectrum is, what a 1D spectrum is, what a 2D spectrum is, and how to compute a 2D spectrum starting from just a 1D spectrum. This is the frequency spectrum. So, in the first section, in there you have to define the type of discretization of your frequency spectrum. So this is the spectrum that you see on the low left image. As a default, you have 25 frequencies, and the minimum frequency is 0.055. So if you divide that number over 1, what it will tell you, what that number is telling you, is that if you leave that 0.055, it means that you are only going to model when you, let's say that you have your boundary conditions, you have your C state that you want to simulate. You have an HS, a TP, and a mean wave direction. If you leave that number at 0.055, if you divide 1 over that number, it will tell you 0.55 that you are going to model waves of up to 18 seconds. Meaning that if you are in an area where you are expecting long swell to arrive, and long swell, I mean waves with peak periods longer than 18 seconds, it is not common, but it's not impossible. And in many parts in the world, for example, in the North Atlantic, you can see waves of 20 seconds or 21 seconds. But what I'm saying is that if you're, for example, interested in constructing or doing something in the Mediterranean, because it's an enclosed basin, you don't have a lot of long waves. The waves in there reach periods of, I don't know, up to 15 seconds, 16 seconds. So in this case, the minimum frequency that you are going to model is enough with this 0.055, because you will be modeling waves of up to 18 seconds. And then you will have all the energy that can happen within that area. But for example, if you are on the northwest coast of Australia, in that area you have very, very long swell waves coming from the South Pole that travel in a straight line towards Australia. And what happens that those waves have periods of up to 20, 21 seconds. So if we leave this minimum frequency as a default, what it will happen is that when Mike is computing my theoretical spectrum that I have passed, any energy that is within 18 seconds and above will not be modeled. And then your results, once the runs are completed and your results, and you try to compare your data against the measurements or whatever, you may see that it's like, I am missing energy. My model waves are way smaller than what the buoy is saying. Is the buoy wrong? It is more than likely that you chop or trim the energy that you should model in that area. So my recommendation for all of you would be, prior to setting up the model, have a quick idea of the area where you are going to work, have a quick look to what type of, based on what Dr. Samir explained to you last week, based on frequency tables, just on frequency tables, what are the longest periods that you are expecting to happen in that area? And knowing that number, just go back to the minimum frequency and just change it to a number that for sure will include those longer periods. As simple as that. The frequency factor, I wouldn't change it because it's just the base number for Mike to compute those 25 frequencies, for example, that you have defined. So I wouldn't touch that. Regarding to the number of frequencies, again, 25. It depends on what you want the results for. For example, for coastal engineering, having 25 frequencies is good enough. But for example, if you're working in the offshore contractor business and you are in a construction vessel, and construction vessels are extremely sensitive to the wave period, because depending on the shape of the hull and depending on how that vessel is orientated regarding the incoming wave, that vessel may suffer a lot of motions, and a lot of motions that may imply people dying or breaking equipment. So you really need to make sure that your weather forecast for that vessel is as correct as possible and as accurate and discrete as possible. And in that case, you will need way many more frequencies, because you really want to make sure that when the wave with the resonant energy hits the vessel is in a safe position that cannot start rolling or doing that. So everything, as I said before, everything is down to what you need the results for. For coastal engineering and for cases that you don't need to output the wave spectra itself. So for cases where only integrated parameters are needed, 25 frequencies will be enough. And the same goes with the directional discretization. The finer or the more number of directions that you create, you will have a way finer spectrum, and then you will discretize the space in way smaller bits. That's good. The more directions that you've got is the same thing as with the frequencies. The more frequencies that you've got, the more accurate or the finer you will define your 2D spectrum. But it comes at a terrible expense, and is the more frequencies and the more directions that you have to multiply those two numbers, and that will tell you how many simulations or Mike will have to do for that single CS state. So if you multiply that time for the entire length of your time series, I don't know if you want to model 20 years or 40 years, that may be a lot of time. That makes it just unfeasible for you to run. So you have to decide in there, okay, I can go with a bit less of, basically in this area, the waves are coming from 3 sectors. So with 15 directions, I'm okay. And then you go to another area and it's like, wow, I have swell coming from these 2 directions, and then I have another swell from this direction, and there is a reef or an island that does a bit of sheltering, and there is some diffraction. I will really need to be very discreet, and I will really need to see what happens when you pay attention to little increments in direction. In that case, you will have to increase it. But again, the choice is yours. And remember that the more frequencies and directions, the longer it will take to run. Separation of wind, sea, and swell. Do I have it here? Yes. So the other one is the separation of wind, sea, and swell. So basically, the other day I was telling you that Mike, you are imposing a certain wave spectrum at the boundary, but then you also need to give wind. Because if you're imposing a wave at the boundary of your model, and let's say that it's a big model, and you're not imposing wind, there is no energy input to the system. So basically, you have the waves traveling within the domain at their own expense. The only energy that you have in there is what you impose at the boundary. And if you remember the equation, the transport equation, that on the left hand you had how the energy moves within the domain, and on the right hand you have the sink and the source terms. In the sink and source terms, you don't have any source. You don't have wind to keep those waves growing. or traveling. You only have dissipation by friction, dissipation by stiffness, dissipation by braking. And what happened? That after a few time steps, that wave condition or that boundary condition that you were imposing at the boundary will decay and die. Because the waves, the only thing that they can do is lose energy, unless you give them a bit of energy to travel. And here it comes the concept of wave age. So starting from a flat surface, the wind starts blowing and it starts creating waves. And what happens? I told you the difference between wind, sea, and swell, right? I told you that the wind, sea are those waves that are generated by the local wind. So as the wind is blowing, the waves are starting to grow and to generate. And those are wind waves. But there is a moment when the wind speed is strong. There is a moment when those waves grow so much that they get to a point when the speed of those waves is equal or greater than the wind that is creating those waves. And what happens at that point? That those waves stop being wind sea waves to become swell waves. And you remember what I told you the other day about the swell waves, that swell waves are not affected by the local wind. And since they are not affected by the local wind, the way that physics, atmospheric physics, interact with those waves is different than when the waves are wind sea, when you have smaller waves, because the wind has more effect on the shape and the period of the waves. But when those waves grow so long and they become swell, then the wind does nothing to them. And this is the way of there are many in the past. I told you that there were many different ways of doing this split between wind, sea, and swell. Usually or historically, there was a non-written rule that all the waves above 8 seconds are considered as swell, and any waves below 8 seconds are considered as wind sea. But that is a very generic approach that in many parts of the world do not hold. So you need another approach. And the best one to do that separation is this one, the wave. So my recommendation would be to leave that parameter with the default setting. You can play with other ones, but if in the end you are interested in just integrated parameters, it's not going to give you any headache. You will not have to justify anything weird. And based on my experience, this is up to date the best way of computing the difference between wind, sea, and swell. Good. So this was the wind forcing. In wind forcing, in that section, you will have to specify whether you are going to impose wind or not. You know what is going to happen in your model if you don't impose wind, that after a few simulations or a few time steps, all the waves will die because you don't have any energy to support the travel of those waves. And those waves have to be the 10-meter elevation wind from the reference level, which is the mean sea level. That's the information that all the formulas in all the wave growth and all the wave transformation models are embedded. They make use of wind that is set or is specific of 10 meters above the mean sea level. Regarding the growth parameter, I wouldn't touch these ones either. You may get for sure if you change the type of earth interaction, for example, or the wave age turning parameter, your results locally will change. You will have different numbers, but those parameters are basically there is no justification for you to change them or tune them unless you have measurements, and that's the only way of fine-tuning your model against the measurements, just by changing those numbers. But I have never seen anybody achieving a calibration of a model against measurements, making use or tuning these numbers. So again, I will not touch these ones. Effect of wave specific wave diffraction. Okay, so in here I am aware, or I'm aware, I would like to be aware, or I will assume that you all know what in physics diffraction is. In this case, is well, following the laws of physics for light. For ocean waves, we have the same problem. When the wave field arrives to an area that on the lee side of that structure is a calm area, what you will get is the effect known as diffraction. So this is, for example, in the top left image, we have some waves traveling from, let's say, north southwest, a wave field of, let's say, swell waves coming parallel to the coast, and they reach that breakwater. So what happens is that when those waves reach the tip, there is a discontinuity in the water layer in there, because you have right out of the tip, you will have a wave height of, I don't know, 5 meters, and right next to it, you will have a wave height of 0. This is a non-stable regime. You cannot have a vertical wall. You will never see that out in nature. You will having a significant wave height of 5 meters, and then all of a sudden 0 meters. The thing is that when that happens, the wave that is next to the tip, or not next to the diffraction point, will have to give energy to the side in order to create a smooth transition between the calm area and the non-shelter area. And what happens with this? That this is a very complex process. It is not that it's not understood, because it is understood, but the problem is that due to the nature of Mike 21, Mike 21 SW is a spectral wave model, or what we call in this discipline a phase averaging model. A phase averaging model, what it tells you is the output is basically statistics. It tells you about the wave spectra and statistics. So it tells you how many waves will be greater than this value, or how many waves will be lower than this value, how many waves will have a period of whatever. But it does not tell you, for each of those individual waves, what the phase is. If you remember from the first lecture, when we were defining a regular wave, for a regular wave, you just need to define a frequency, an amplitude, and maybe a phase. Mike 21 SW, the equation that it's solving, does not allow you to solve the phase. And solving the phase, which will tell us where the crest and the trough of that wave will be for a certain location, because all those things are I will say it, are affected by the local water depth, for example, and you need to know that. Mike will not be able to compute that. There are other programs that compute correctly what is happening at the lee side of protected areas, for example, harbors, or at the leeward side of an island. Let's say that you have an island here and all the waves are coming from the north. So all the waves will hit in here, but at the lee side of the island, you will have a very calm area, because those waves will travel around the island, will diffract a little bit, and will travel a little bit toward that calm area, but there will be very little energy, because the rest of the energy in Mike will keep traveling. But if you're interested in knowing what is happening in that area, you need to model that area specifically with other type of model, which can be a mild slope program, or a busyness model. The main thing that you have to take in here is that Mike can resolve wave diffraction, but only in an approach manner, which means that it only works, let's say this way, if in your model you have, let's say, an island in the middle of the domain, and what is happening right behind the island is not of interest for you. So it will effectively compute how much energy is lost when doing the diffraction around the two sides of the island. But what you are going to get from that is very little. The changes in the wave energy are going to be very little, because Mike SW cannot compute it properly. So bottom line in here is, don't use wave diffraction in Mike SW for two reasons. The first one is that the results are not good, but it is not because it's Mike, because any other phase averaging model, like Telemach, for example, or Swan, or whatever, they have exactly the same problem, because it's just due to the equation, to the nature of the equation. Don't use in these models wave diffraction, because it's not well solved, and second one is extremely time consuming. So you will see you can run a simulation with a dummy test, including wave diffraction and excluding wave diffraction. You will see that the difference in computing time is huge. And since it's not going to model it properly, don't use it. Good. All the things that you need to know in here is the other day I was telling you about the energy spectrum, which is divided in frequencies. We're not talking about dispersion or the 2D model with the frequency, with the directions. Here we're just focusing on frequencies. Then I was telling you that within a C state, as the energy is distributed over a range of frequencies, there are nonlinear effects between all of those waves for that C state that they interact with each other. And there are basically two ways of interaction for the waves within the same C state. There are two main nonlinear interactions. The first one is called quadruplet interaction. And the second one is triad interaction. I'm not going to bore you with the details of or the mathematics behind this, but basically what this is telling us is that when you are in deep water, or when your model covers up to the offshore region, in that area there is a very important physical effect, which is that the smaller waves transfer their energy to the longer period waves. And it happens in groups of 4 waves. I will not go into detail of why is this, just have to believe me. And if you want to know more about why is this, I can give you a reference, a very nice book from Holthausen where it is explained. I'm not going to go into detail of that in this presentation. Basically, what I want to tell you is that for the quadruplets, for a given C state, what you will have is quadruplet is the big one in here. Is that this is the energy spectrum. This is the frequency. When we are moving into higher frequencies, that means we are going into lower or shorter periods. And in this area, what we've got is the opposite. We have smaller frequencies, which mean long periods. So what happened at the offshore area when the waves are starting to travel within my domain? That for a given C state, energy in the higher frequency part of the spectrum will be disappearing, as you can see here that it goes negative, and will be transferred to the lower frequencies. So basically in the offshore area, the smaller waves will disappear, but that energy has to go somewhere. And where is it going? That energy is transferred to the shorter or to the lower frequency part of the spectrum. Basically, the long waves will eat the energy from the small waves and will keep it for the longer waves. And those waves will grow even longer. And in nearshore, you have the opposite effect. In nearshore, it's the same thing, but instead of having interaction of 4 waves, we have interactions of 3 waves. And the effect of that, this only happens in very shallow water, is that the energy contained in some of the low frequencies is transferred to the high frequency. So the swell waves, let's say this way, will diminish or disappear from the wave spectrum in the shallow area, and they will give their energy to the shorter period. And this is very important if you are interested in nearshore currents, because the nearshore currents are completely driven by the currents generated by the wave breaking. But what happens in here? That first, the triads, although they are well understood, in modeling, their contribution is not that important, let's say this way, in the sense that it gives you kind of a number, but it's not strikingly accurate. And second is that it takes ages to compute the triads, whereas the quadruplets are extremely fast to compute. If you do a test in Mike with and without triads, what you will see is the main thing that you will see here is that, especially if you have a very shallow area in your mesh, where the model has to struggle with very little water level, you will see that your computational time just rocks. So unless you have a very good reason why to output or calculate the triad interaction, because we're interested in the very shallow water nearshore current, don't use them. But the quadruplets, you always need to include them because it's one of the most important nonlinear effects of the waves nearshore. And that internal transfer of energy between lower frequencies and higher frequencies will have a massive impact on what is happening to that sea state near the coast. Okay, we are almost there, just 2 slides to go. Other concepts that we need to show in here, I guess that you are familiar with them, but then I will just refresh your mind. The first one is wave shoaling. So we know that wave shoaling is basically an effect that happens when the waves transition from deep water, intermediate, and shallow water. When the waves are in deep water, the water depth compared to the wavelength of a wave. Let's think of a regular wave to make this concept simpler. When the distance or the water depth is more than half the wavelength of that wave that you're considering, it happens that it is so deep in there that the wave, when it's wobbling, when it's going up and down, it's so far from the seabed that it will not feel. It's like there is no bottom for me in there. The wave is not generating any interaction. But as you go into shallower water, when the wave goes up and down, it will start feeling the bottom. And this is very intuitive for you to understand that as you go into shallow water, what happens that the wave will not be able to go down when in the step from going from crest to trough. It will start not having room next to the seabed to allocate all of that water, whereas the crest will increase in order to allocate all of that water. And what happens that is basically is showing you wave growth near the coast. That's what happens. You know all about this, that those waves cannot increase indefinitely. You will not have a wave height near the coast of 100 meters or 20 meters. There will be a moment when the steepness of that wave, which is the steepness is the ratio between the wave height and the wavelength, is telling you that the base of that wave is so narrow that the water molecules cannot hold the weight of the wave, and then it will collapse. So this is the main wave breaking parameter or control parameter, the steepness. If your steepness goes above a certain ratio, they will break. Wave shoaling and wave breaking. Yes, going back to Mike. Mike, I think that you have an option to define the limiting ratio for you to define what's the maximum water depth that you will allow in your model for your wave to exist. For example, if you have 1 meter of water depth and you have a wave of 1 meter, you can easily imagine that there is no physical way for that wave to go up and down in just 1 meter of water depth. You will need at least half of it for the wave to be able to go up and down. So basically that limit, which is theoretical and it will never happen, is a relationship between your wave height and water depth of 1. But that doesn't happen in nature because there are other nonlinear effects that will not let this happen. What it has been observed by the U.S. Marine Corps of Engineers is that there is a limiting. They have never seen waves that related to the local water depth have a ratio above 0.78 or 0.8. So bottom line for you is I would not touch these default parameters because they are so well established in the literature, and they are so basically they are applicable everywhere in the world that unless you have measurements and you really need to nearshore measurements and you need to be strikingly accurate with your model, we may consider tweaking this number a little bit, but that's not the usual case. Bottom line, leave it as it is. And the last two concepts, bottom friction. So how does bottom friction affect your simulations? So as I've been telling you so far, when you are in deep water, for example, here in this slide, what we can see is that the motion of the water particles within the water column is basically a circle. That is because the surface is so far from the bottom that it doesn't feel the bottom. So basically, what you have is the natural decay of the energy transferred from the wind to the sea surface at the top. And as you go down the water column, it starts decaying because energy starts dissipating just by friction of the water molecules. But there is nothing else. So you have orbital motions. So the thing is that regarding the bottom, you don't have any bottom friction or bottom dissipation because the waves are so far that they don't float. But when we go into shallower water, what happens? That circular motion starts to interact with the seabed. And interacting with the seabed, it will start suffering from drag, suffering from friction. And then those circles will start becoming kind of an ellipse, going back and forth, going back and forth. And if you put a thermometer, for example, next to the to the seabed in that location, you will see that the temperature basically increases because the water is pushing back and forth the sun in the area, and it will have an increase in temperature. It will be negligible, but you will see the effect just because of friction. So the thing here is that you have different ways of defining the friction in Mike. Usually we use the standard or the default friction setting, which is, I think it was Nikurat's 0.4. But in case that you want to be more accurate, and for example, you are designing a harbor or doing some beach nourishment studies, and you have survey data, you have measurements, you have a description of the sediment, of the local sediment, then Mike allows you to make use of different formulations which are based on the type of sediment that you have in your area. One of those parameters that you will need to know is what we call the D50. So this is when you're doing a granulometry test, basically you're characterizing the size of your sediment, and the D50 is basically the median size of your sample. So with that value, you can go to Mike, specify that value, which is diameter, which is millimeters. So this is related to the size of the sediment that you've got. And also, you can specify the type of sediment, whether if it's sand, if it's mud, and then it will try to compute, Mike will try to compute a much better friction coefficient, because now you are telling Mike exactly how the sediment at that location is. But if you don't have any information about the D50, as I said again, with the default value, you should work. That's the default value. If you're trying to tune or to calibrate your model, the friction parameter is a parameter that you should play with in the beginning, because friction in shallow water or intermediate water has a non-negligible effect. And you may see that if you increase that default value a little bit, you will have more friction and your waves will lower, or you can do the opposite thing. You lower that friction coefficient, meaning that you will have less dissipation and your waves will grow bigger. And then you need to just fine tune that parameter in order for you to match whichever measurement you have in the area. Always within recommended values. It is not that if the Nikurat's value is 0.4 by default, not just because by using a number of 5 that gives you for your specific case a perfect match, it does not mean that it's right. Because a Nikurat's number of 5 is basically nothing can move. So always bear in mind, you can fine-tune this number. You can easily find in literature recommended values of friction for certain areas. If your bottom is either sand or mud or cobble or rocks, you will find literature in there giving you recommended values or ranges of values that you can use. But again, this is a parameter that you can modify yourself and see the effect, which is basically going to give you higher or lower waves. And then up to you to select the most accurate value based on if you have local measurements or based on just a scientific judgment. It's like, well, this coefficient is still too big, we cannot justify it. Or it's within the limit, we will go with this one. And last but not least, this is another option that is given in Mike. This is extremely important for offshore waves. And to be honest, I don't know why this is offered as for you, for the user, to be able to tweak it, because basically you shouldn't tweak this one. You should make sure that you always include the wave, the white capping, because this is the way. The white capping is the way for the waves to balance the energy in the sea state with what is happening with all the physical effects or the physical agents that are happening within the area for the waves on their way from the boundary to the target area. Because the same way that shoaling and breaking controls what happens to the waves near shore, and the breaking happens because there is little water depth and the waves shoal until they get to a limit that they have to break. In deep water, you don't have that limitation. In deep water, we said that the waves do not feel the bottom. The bottom is so far from the surface that they don't feel the bottom. So waves cannot break due to the bottom. But if you go on board of a vessel and you have been unlucky enough to go on a cruise and then having to cross a difficult sea or a storm, you see that waves are still breaking in the middle of the ocean. But the thing is that the mechanism is not the same. It's not due to shoaling. It's not due to the seabed. It's just due to the fact that they are growing so big that their steepness is getting smaller. The ratio is getting smaller, and then it's the mere weight of the wave which causes them to collapse. So they start, let's say, crumbling from the tip, and it generates those white foam layers that you see in the water. But again, this breaking is due to a steepness offshore. It has nothing to do with shoaling or the seabed. And this one is very important. So you always need to make sure that white capping is included in your model. Again, you have access in the white capping formulation to, I think it's one or two different formulations. I can't remember right now, excuse me, where you can change a little bit those coefficients. If you decide to change those coefficients or play with those coefficients, it is okay. It's okay in the sense that if you decrease that number, you will have probably less breaking, so you will get higher waves. And the opposite, if you increase that coefficient, you will have less higher waves in your area. You will see it. You will see it with a sensitivity test. You will see it with your own eyes. And now the thing is that you will have to justify with offshore measurements or whatever that by modifying that coefficient of white capping, you get what the measurements say. Only in that case you can start playing with that coefficient and give it a physical sense for you. Otherwise, I would leave the default value, but for sure you need to activate white capping. Otherwise, you are more than likely, if you don't activate white capping, basically what you are saying is that no waves are going to break offshore. So you're saying that all the waves that are entering the model in the deep area, they will make it to the shallow area. And what happens in that? And what you are going to say is that since no waves were breaking offshore, when those waves get to near shore, you will have more energy, you will have more larger waves that happen in reality. So your model results will not look like reality because you're saying that no waves were breaking offshore and all those waves made it to nearshore, when we know that waves break offshore due to white capping. The bottom line, don't forget to include white capping. And the second advice is, if there is no other way for you to tune your model, you can try playing a bit with these coefficients, but you shouldn't vary them too much. I think that's it. I think that I went above the presentation time. Sorry for that, Dr. Samir, but I think that now with this with this one, we are done.
Thank you, Robin. Is there any questions, please? We have some questions, Robin.
Yes, I'm happy to tackle questions. If not now, after the presentation. So I let people take a break and have a coffee and decompress.
I asked for the time formulation and the spectral formulation. You mentioned that the domain side is the main decision factor for the formulation. You are right. So if the domain size is less than 50 kilometers, 50 square kilometers, I must collect or decide the picture quasi-stationary formulation.
Mm-hmm.
You mean that?
Yeah, well, I didn't hear the question very well. There is a lot of echo, but I think I got it. So let me go back to the presentation. You're talking about the solution technique, right? Between low order and fast order. Sorry, low order and high order, right? Or was it the, this one? Sorry, quasi-stationary and in-stationary.
Yeah. The domain side is the main concept decision for the formulation. The domain side.
One of them is the domain size, for sure, and it has to be computed. You can check that number very quickly, in the sense that let's say that you create a model mesh. You still don't know whether you're going to use quasi-stationary or in-stationary because you still don't know. You set up your model and then you say, wow, okay, the outer boundary of my model is, let's say, 50 kilometers far from the coast. And then you may say, wow, this is relatively a long distance. So it may be that I need to use in-stationary formulation instead of quasi-stationary. You are more than likely to do that. But my recommendation would be to, you have your outer, let's see if I have, no, I don't have a picture here. But basically, let's say that this is an operation that you can do very quickly with pen and paper, which is you take your model, you measure the distance from the most offshore boundary to the coast. You measure that distance in kilometers, whichever is it, 50, 70, whatever. And then what you have to do is you have to go and pay attention to the time series of wave parameters that you are going to impose at the boundary. So these are the waves that you're going to impose at the boundary of Mike in order to transform those waves to nearshore. And in there, you have to take a look to all the wave periods. You can take a look to the peak period. You take a look to all the peak periods that you are going to simulate. Okay, so one time step will have a peak period of 10 seconds, another one of 12, another one of 7. And then with that period, what you can calculate is very quickly. You can do a quick number and assume that the waves are always in deep water. And in that case, the celerity of the wave or the velocity of that wave will be 1.56 times the square of the peak period. I repeat, if you take the peak period of the wave, you square it and multiply it by 1.56, it will tell you the velocity of that wave, at least in deep water. And then you can do a quick calculation. You divide the distance that you measure from your model from the outer boundary to the coast, which is, I don't know, 70 kilometers. And you divide it by the velocity that you just calculated for the wave that is going to take longer to travel from the boundary to the coast. So you have to take a look to the smallest peak period in your time series. And when you divide the distance by the velocity, you will get how much time it takes for that wave to travel from the boundary to the coast. Let's say that that time is 30 minutes. You compute that quick number, and it says 30 minutes. Now you take a look to your boundary conditions, and you're telling me, okay, my model is going to be fed with new boundary conditions every hour. Let's say that you have a time series of hours with values on the hours. And then you can say in this case, okay, for my smallest wave, it only takes half an hour to travel the entire domain. Whereas I am updating the conditions at the boundary after 1 hour, which means that my waves are fully modeled before I have to update the condition at the boundary. In that case is when you can say, I can play it quasi-stationary because the waves are taking so little to travel from the boundary to the coast that it's not affected by whatever I'm updating at the boundary every time. But let's go to the opposite case. Let's say that now you compute, you have a distance of 70 kilometers, and the velocity of the smallest wave is going to be, I don't know, 1 meter per second. That will give you, for example, a ratio of 3.7 hours, which means that, okay, for the smallest wave that I'm going to model, it will take for it 3 hours or 3.5 to go from the boundary to the land. But the problem is that every hour, I will have to update the forcing conditions at the boundary. So in the time that that wave took for it to go from the offshore boundary to the land, 3 different boundary conditions have happened at the boundary during that travel, which means that you cannot use, in that case, quasi-stationary formulation. You need to use unstationary because the boundary, by the time that the previous waves are traveling, the boundary will be updated, and that will have an effect with the waves that are already in the domain. Is the way of crunching this number, this rough number, easy to understand? Because with this operation, you will have a clear idea on whether you can use quasi-stationary formulation or not. Basically, the thing is that deep water and shallow water are relative concepts. For example, if I have 1,000 meters of water depth and I have a wave height of 1 meter, that ratio is so small that that wave of 1 meter is in deep water. It's so small compared to the water depth that it doesn't feel affection. But if you take 1 meter wave and you examine it in a water depth of 2 meters, then you will see that the same wave at a different water depth, it goes into a different regime, which is the shallow water. And that's what affects the speed of the waves, and that's what affects the transformation of the waves. But for you to have that criteria or that quick criteria, shall I run it quasi-stationary or unstationary? Just measure the distance, compute the velocity of the wave with the shortest period that you're going to simulate, and see if it's going to take more or less than the frequency that you update your boundary conditions at the lateral boundary of your model. Does it make any sense?
Okay. For the diffraction, you mentioned that it's not recommended to use the.
Excuse me. Can I ask a question before going to the next point of the Engineer Ahmed?
Absolutely.
What I understand from you is that in stationary is more accurate in general, but the computational time is much more.
So,
is it correct?
In a station, I mean, if both formulations are used in the right context, they will give you both the right answers. The problem is when you make use of the assumption in the wrong scenario. The thing is that for quasi-stationary formulation, as I said before, if you have a small domain and the waves that you are imposing take way less than to travel within the domain, way less than the update of the boundary conditions of the lateral boundary, you can use quasi-stationary, because the computation of each time step or each t state will be basically independent of what is happening before and after. And because of that, the computer has to do way less computations and it will run way faster. And if your domain, as I said, anytime that your domain is small and you satisfy this condition that the smallest way will take less to travel from the boundary to the land, then you update the boundary conditions, then that's fine. And you will get results from the model that are correct. Why? Because the physics, the restriction, the Courant number applies in there and it's satisfied. So your solution will be perfect. But if you apply that scheme in a wide area where the smallest waves that you're imposing at the boundary will take way much more time to arrive to land than the frequency that you are feeding the boundary of your model, that will be wrong, because you are saying that the waves basically transform from the boundary to the coast instantaneously. They are not affected in the passage of time for those waves when they are imposed from the boundary to the land. They are not affected by anything else. And that's what I told you. You can interpret this as reaction time. I mean, if an event happens or takes too short to happen, there is no time for the system to do other things or to interact with other things. It just happens everywhere at the same time. But if your domain is very, 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 very big, your actions within that domain will not be able to impact all the things that are happening all over the domain at once, because you will need time for that information, for those waves to travel from that point to the other. And that's the reason why you have a very big domain where the conditions at the boundary are updated way more faster than what it takes for the waves to travel. You need an stationary. But stationary, a small domain. Just crunch that number and then you will be happy. The good thing, you know that you have to construct a small domain, for example, in a bay area where it's completely protected from offshore waves. So the only thing that you have to impose is basically wind. In that case, you can easily make use of the quasi-stationary formulation. Your domain is going to be small. The waves can only grow based on the geographical fetch and the duration of the wind that you've got, and that will be computed very quick because your domain is small. You make sure that you compute that the smallest wave will take way less than the frequency of updating the boundary conditions, and then that's it. Again, quasi-stationary and stationary, this is a relative concept, not because the model is for you 100 kilometers, means that it's not going to be suitable for quasi-stationary formulation. Everything depends on the waves and the periods that you are going to simulate. If they patch in, if they tie in with the size of your model and the period of your waves, then that's fine. But if it doesn't satisfy this condition that I told you, you cannot use it. So basically, for all coastal applications that coastal engineers do nowadays, when you have to start from scratch and make use of a regional model, for example, that covers 50 kilometers offshore at least or something like that, go for in stationary. And when you're interested in a local model, a small model of near a harbor, or you want to take data from a regional model and create a local model of let's say a harbor or a beach, and you really want to see what's the effect of the currents on how the waves break in there, because your model domain is going to be very small, then you will be able to make use of the quasi-stationary approach. But again, please compute this quick number that I told you. It's just the distance from offshore to land. Take the smallest peak period that you're going to simulate, compute the celerity of that wave, and see how long it takes to travel from the boundary to the coast. If it's longer than the update time of the boundary condition, you cannot use quasi-stationary. If it's shorter, you can.
Okay.
Is this clear?
Okay, great.
Good.
Okay. At the fraction, you mentioned that we it's not recommended to use diffraction at spectral wave.
It is, so as I said, oh, sorry, go ahead.
But in reality, it occurred and affected the current speed and current direction. So significantly, the significant wave height allowed the jettison breakwaters.
Of course. As I said before, wave diffraction is one of the main physical effects and the parameters that you need to properly model and describe when you are, creating a harbor or creating an expansion of a harbor or a marina where you have to create more breakwaters to allocate for more room for vessels or the turning basin. Well, that is very important, as well as for beach nourishment. For example, in areas that are heavily eroded and the sand has been taken out from the circuit, you will have to construct groins, which are basically small breakwaters. And depending on how the waves are attacking those groins, they will cause diffraction around that point, and that diffraction will generate a pattern of currents that will, let's say, distribute or redistribute the sand based on that pattern along the coastline, and it's confined by the groins. What's the problem that I said again? That I said before, that microspectral waves, it's in the name spectral, is, how do you call it, non-specifically disclosed, but it's in the name. It's a phase averaging model. It tells you information about parameters like HS, parameters like TP, parameters like TN. Those are statistical parameters of a sea state of 1 hour or 3 hours, and then you have a description of, I will have, I don't know, 10% of the time waves of significant wave height of 10 meters, and 30% of the time I will have wave heights of 2 meters. You know the statistics, but the program will not be able to tell you how to draw that single wave. Because for drawing that single wave, apart from the frequency and the amplitude of the wave, you will need the phase. And the equation that I have shown you, the energy balance equation that I showed you, does not do that. Therefore, the results from a spectral wave model of a phase average model will never give you information of individual waves, of the geometry. And what's the problem with that? That the geometry on how different waves with different phases, not just different periods and direction, but also different phases. This is from basic physics from high school. You will see that they interact in different waves. And then the wave, the crests and the troughs start to pop up from that interaction will be different. And for example, if you are in a harbor and you are you want to investigate how calm your harbor is, what you want to see is that a certain area, the interaction of these waves that are diffracted, because the diffraction also imposes a change in the direction, right? So let's say that this is your breakwater, and you have incoming waves from north. As soon as they touch the tip, many of the waves will keep traveling in their direction, and the bathymetry tells them to do something else. But the waves next to the tip, they will start, as I told you, the wave height in here needs to give energy to the calm area. So you will start having waves going in this direction, and you will start having some currents in this direction. And that's the problem, that one of the main things that describe the behavior of those waves and those currents is the phase of the wave. And as I said, Mike does not compute that. And since Mike does not compute that, any results that you extract from your model, from your Mike model, near or in the vicinity of the diffraction point will be wrong or poorly calculated. I mean, in generally speaking, and if we take a look from the distance, and let's say, okay, I'm an astronaut, and I am seeing I'm in the International Space Station, and from there I see I don't know, the Azores in the North Atlantic, and then I see some waves coming from northwest, from the North Atlantic, traveling towards Africa. At that scale, at that distance, that's what Mike does. I mean, you can see that some of the energy was blocked somehow by the islands on the way from those waves traveling towards Africa. They hit the islands, and in here, of course, there will be some blockage of energy. but there will be also energy keeping traveling down. Why? Because that energy has not been completely blocked by the islands. But the thing is that in the long scale, you will see that you can get to speed that there is calm on the lee side. I mean, from the International Space Station, you will see that there is calm in the leeward side of the island. But if you go there, if you get closer to there, you will see that it's way more complicated. You have many more waves, but you cannot see them from the International Space Station. So in here is the same thing. Mike can give you an estimate if you are considering the diffraction of, let's say, an island in the middle of the domain, and how that little blockage is going to impact what is happening on the coast. Then that's fine. It can do it. But if you're interested in what is happening right behind the island, or if you have a harbor model in your model, it will not give you the right answer. So for that, what you will need is you will need to set up a different model, a model that is capable of resolving the phase. So I showed you the equation in Mike 21 that was the energy transport equation, which was just the wave action density and then sources and stuff. In there is no information at all about the wave phase. But the equations that are solved by these programs that I'm telling you, like the mild slope equation program, that's something that you can find in Telemac, for example, or way more complicated and sophisticated models like Business. You have in Mike 21, you have a module that is called Mike Business. Those models, the equations that those models solve, they are capable of solving the phase. So when you simulate something with those programs, you will see how the waves distribute and how the crests and the troughs within your domain are distributed. That's something that you cannot do or you cannot see in a phase averaging model, but you can see it in a phase resolving model. What's the catch? That the equation that this model, the Business model or the mild slope equation model solve, the equation is a bit more complicated. And with a bit, I mean that for a single C state, since it has to model all the interactions between the different components of your spectrum, remember that we were discretizing the input spectrum in little cells of frequency direction. The problem is that the way those equations have to be solved is it takes much more effort. And then what's the problem? That while with Mike 21 spectral wave that you don't have to resolve the phase, you can run, let's say, 40 years of 1 hourly C states at your boundary, I mean, as forcing, in, let's say, 5 days or 1 week, if you have enough computational power. That's something that you cannot do with a phase averaging, with a phase resolving model like Business or like mild slope, because it takes way much more time. So what happens that basically you use models like Mike, or the SW model, the phase averaging model, to bring many years of offshore data to nearshore. So let's say, for example, you're interested in designing a harbor. So what you do is you want to bring the wave from offshore to the vicinity of the harbor, and you can do it with Mike 21 SW. And that will allow you to reconstruct 40 years of offshore climate to nearshore in, I don't know, 5 days, 6 days. Once you have that nearshore climate, and you have your layout of your harbor or the stretch of beach that you want to redesign or to recover, then what you do is from this nearshore climate of 40 years of whatever, you perform a statistical analysis. And from that statistical analysis, what you do is, what I showed you the other day is one of the important parts is the extreme value analysis. Because from the extreme value analysis of the variables of interest for you, let's say, for example, the HS, that's what is going to provide you with your design conditions. Remember, while operational conditions is the normal conditions, so this is just very simple statistics of grouping the data in directions or months or whatever, it gives you a bulk idea on how throughout the year the waves will happen or will behave in the area. With the extremes, what you are doing is you are defining the design condition. This is when the structure is going to be built, it has to be built as assuming a certain failure risk. You cannot build anything without any risk. I mean, you can design your structure against more intense and more severe events. For example, the 1-year condition, the 10-year condition, the 100-year condition, and then that's fine. You define your structure to withhold that event. For example, the 100-year wave. And then that's fine. You will say, okay, when I'm going to this, I'm going to design my structure in a way that it withholds the 1,000-year return period wave. That's cool. That's great. I mean, if you design a structure that can withhold or that can withstand the impact or the loads of a 20-meter wave height in your harbor, then that's fine. Then that's great. Very little risk for the people, and you make sure that structure will last in place for, I don't know, 100 years or 200 years. But what's the problem? That this is just the theory. But in the real world, if you have to design, it's not the same designing for the 100-year condition than for the 1,000. Why? Because basically the size of your structure, in order to withstand those loads, will have to be way bigger. And with way bigger, we mean more material. And with more material, we mean a bigger extension. And with that, we say a lot of manpower needed, which means a lot of budget. So that's the reason why you cannot, you always have to model, having in mind the design life of your structure, and then based on the results from the phase averaging model, you apply the extreme value analysis in there, you compute your design return period that you want to use to design your structure, and then you model those cases, those individual cases. Like, for example, you want to model the 10-year wave condition coming from different directions, from 30 degrees, from 0 degrees, from 330, from 300. Then you can simulate those single cases with the model, because one of those cases will take you maybe 6 hours or 7 hours. That's the reason why you cannot use it for general. You cannot use Mike 21 you cannot use the mildest low program or Mike Business to run all the cases, because it would not be finished in 100 years. Those are more accurate programs that calculate every single wave, the behavior of every single wave, but at the cost of taking way much more computing time.
So on the other hand, it's recommended, is that recommended to use the diffraction in the coupled model, or you recommend using Bose-Einstein?
Sorry, I didn't hear well. There's a lot of echo in the room.
If we using the coupled model, okay, is that recommended to you use diffraction or not?
I cannot hear. I hear about the diffraction, but I don't hear the first part of the.
The coupled model. If we applying or using the coupled module for dynamics, vector wave analysis, and the sediment transport. So it's recommended. Is that recommended to use the diffraction or
not? Dr. Samir, can you or can you come closer to the mic, because I cannot hear the first part. I don't know what it's a lot of echo. Is that the communication, not the question itself? I cannot hear it.
قبل الموديل ويف مع سيدن مع هيدروجين ينفع الشاب الديفراكشن ولا لا ولا لازم حاله الديفراكشن دي محتاجه بوزنس بس.
Engineer Ahmed asking about in case he is trying to solve a coupled model covers sediment and hydrodynamics and waves all together.
Yes.
In that case, it is recommended to use diffraction models like Bose, or it is more recommended to use SW models.
So again, if let's talk about design phase, where you have a certain layout, or you, let's say that you're working for a contractor or for the client, and the client has let's say 3 ideas for a certain harbor. So I'm going to design a harbor, but I don't know if it's going to be like this, or like this. So basically, once you know those layouts, you know what you do is you model the 3 of them. And then what you do is you compare the results for the 3 of them, and then you will see which one is giving you the best or the most ideal conditions for your operation. And in that case, you want to be as accurate as possible. And for that, you need, in order to successfully test those layouts, you need a phase resolving model. You don't need Mike for that. Again, you can use Mike to bring offshore conditions to nearshore, but when these effects like wave diffraction, wave diffraction and intense braking happen, then Mike SW is not enough to give you the detail that you're looking for. Well, so that's the thing. Whenever basically you're going to design a harbor, that's or an LNG terminal where you have structures and they cause diffraction, and the thing is that you are going to moor you're planning to moor a vessel on the lee side of the breakwater in order for it to have calm and not be affected by the waves. You need a diffraction model, and that's not Mike SW can give you the information what is happening in front of the breakwater, but what is happening behind is not going to be accurate. You need a model that properly models diffraction, which is Mike Business or the Miles-Slope equation program. Was it that?
So another question about the wave interaction. What
Yes.
is the difference between the triad wave interaction and the quad Rapley wave interaction?
Yes. So as I said before, I'm going to be scientifically accurate. Both interactions, quadruplets and triads, happen both in deep water and in shallow water. But when we compare the orders of magnitude of their impact, quadruplets are extremely important offshore in deep water, whereas triads are way more important or have much more weight or much more a bigger order of magnitude that the quadruplets. So offshore, you need to pay attention to the quadruplets. And with offshore, I mean deep water. And near shore, in case that you can afford the computational time that adding the triads is going to cost, then switch on the triads. Especially if you are going to investigate the shallow water, the near shore shallow water current patterns, you need to have the triads because the triads contribute to the current pattern. But only if you are interested in very, very shallow water, I don't know, 1 meter, half a meter, something like that. And for that, you will need a very high resolution mesh. And then you will need to make sure that you have a well-defined bathymetry. That's up to your judgment. Again, if you are interested in this system of near-shore currents that are induced by braking, include the triads. But bear in mind that computing the triads is going to take a lot of time. You can do the test running 1 month of simulations with and without the triads, and you will see the impact. But for sure, offshore, always use the quadruplets. Do not forget.
Okay, we had another question about the braking. What is the about the wave braking?
Wave braking, yes.
For the Egyptian coast, and it has a special wave profile slope. What the recommended equations for the Egyptian coast? Nelson or Rosenix or specified gamma for our Egyptian.
So you are talking about the different. Let me see. I can open my run mode. I need mic in front of me, otherwise I will not be. SW. Spectral time, we go to white cutting, wave breaking. Okay, so we are here. And what was the question again? You have you can use wave breaking or no wave breaking.
What is the recommended equations for the Egyptian process?
The difference for the difference between the equations of these gammas, the functional forms are not are in let's say in misuse, because the specified gamma you define it here, and this number, which is 0.8. This ties in with exactly the number that I told you that is recommended by the U.S. Marine Corps of Engineers, which is, let me see, where did I put this? Here, which is that number of 0.78 that is rounded to 0.8. You can play with that number. I mean, in the majority of the laboratories, this number is smaller. You need it's a smaller number, because you need a bit more of water depth than the wave height itself in order for that wave to occur. But I mean, you can play with this number if your results improve and make your model match the local measurements. You can make it down to, I don't know, to maybe up to 0.5. I have used 0.5 in the past if I needed to, because it's justified. But for sure, nothing bigger than this, because there is physically no space for the wave to go up and down in such a small water depth. So basically, just leave this one. If you're talking about constant and varying domain, if you set this option to constant, what it will do is that in every single node within your mesh, in every single node where the computation is carried out, it will always consider a gamma value of 0.8. If you go for the varying domain, basically what it is that you will have to provide to Mike a map. It doesn't have to have the same resolution or shape than your mesh, but for sure it has to cover the entire domain of your mesh. And in there, what you can specify in the different nodes or in the different points, you can specify a different value of the gamma. For example, for one location, you can use 0.8, and for another one, you can use 0.72, because it represents better the breaking of the waves in that area than the other. But that is a map that you will have to construct yourself. It is not difficult, it is not rocket science, but you will have to create it yourself. And
So
to be honest, based on my experience, I have only done that a couple of times. Usually with the
So it's related to the breaking line in every loop.
yes,
Right?
yes. So yes, because that defines the start of your breaking zone. Remember, where waves break, it is not a single point in the space where all of the waves break, because the waves have different frequencies and different amplitudes. So there is a range of water depths when they start to break until the coast, when all of them break, and that is defined by that number.
Thank you, sir.
My pleasure.
Okay, Robin, thank you for this session.
My pleasure.
What is your recommended time to start your contribution in data sources?
I have only, because I thought I was going to be able to add another source, but it seems to be, at least for the time being, down. So I'm not going to introduce more data here. I have basically three data sets to share with you: CFSR, NOAA WaveWatch 3, and the CFS system. It's just 3 slides, so I can always do them after yours.
So just I would like to arrange the schedule. We'll have a break, lunch break around after our lunch break will start after 45 minutes.
After 45, okay, quarter to 12 here in Denmark.
Yes, and this break will be around 1 hour.
1 hour, okay. So
What is your way to start your session after the break?
okay, so that is you will start around quarter to 3 your time.
Excuse me?
So you are starting again after 1 hour and 45 minutes.
Yes, you will start.
Me in 1 hour and 45 minutes.
Yes.
Okay, I can do it.
You can start now. I can start now, and then you start after the break.
Okay, that sounds like a plan.
Such that you take a break.
Okay, fantastic. So I will see you again in 1 hour and 45 minutes.
Great.
Cool.
Thank you for your session. It was very, very nice.
My pleasure.
Thank you. انا هنعمل تشينج شويه نغير شويه. انا ان شاء الله هنبتدي مع بعض في موضوع ممتاز، موضوع جميل جدا جدا ملوش علاقه بالموديل، ملوش دعوه بالويبس، بس كلنا هنشتغل اونلاين. الموضوع ببساطه ازاي تجيب الداتا اللي انت عايزها. يعني انت عايز تجيب ويندوز داتا، عايز تجيب سيرفيس ريفيجن، عايز تجيب فاهم، عايز تجيب سيلينتي، عايز تجيب من على المواقع بتاعت الانترنت. فده التوبيك بتاعنا. انا حبيت ابتدي انا الاول على اساس ان انا اقطع، يعني انا بقف لما البريك بتاعنا يجي على طول. انما هو لو كانت كده فممكن الموضوع يموت وفي ايه. فعشان كده بعد ما نخلص الجزء بتاعنا انا في كذا موضع هشرحهم لحضراتكم، وبعد كده هشرح على حسب الايه شير سكرين ويندوز. بعد كده data source useful model.